The first thing we need to make great.
You might sound like
Still bad. I'm surprised that it's.
I had 8 people, maybe 2. It's totally right. But like, someone in the second period folks.
What are you gonna take off?
It's like. You can look at practice.
You guys need to stop finishing the first semester.
Yeah, someone in the second period told me that like.
Okay, I see a couple of slots missing. For those who haven't posted their phones, you can get your phones. Okay, yesterday we did addition and subtraction and scalar multiplication for matrices. I feel that's pretty straightforward. I think, you know, being able to just understand that every matrix has its own size and dimension, and being able to match the corresponding locations to add matrices. I feel like we didn't struggle with that yesterday. So today we're talking about multiplication between matrices. So we'll spend 2 days on this. And then the verifying portion and inverse portion will be that next week on Monday. Okay. So if you guys can turn to page 5 in your packet. This word problem here should be at the end, so we'll come back and do the matrix multiplication problem, the word problem at the end. But I want to start off with, if we go to the middle of the page here. And just talk about how the process is going to be when we multiply matrices. So matrices can be multiplied with each other if the dimensions are not the same, but they need to have a certain relationship with each other. So let me just read the notes and then I'll go through it step by step. To multiply matrices, multiply every element from one row in the first matrix by every element from one column in the second matrix and find the sum of the product. This gives you the element in that row and the column in the answer matrix. So I'm going to set this up so that visually it will be helpful to see exactly where the parts will go. But first, we have to understand that the first matrix is going to be the one on the left, and the second matrix is going to be the one on the right. Let's find the dimensions of each of these matrices separately. So we know that every matrix is going to be created by row and column. So what's going to be the dimension of this left matrix, this first matrix? Good. So 3 rows followed by 2 columns, right? With 1, 2, 3 rows goes horizontally and columns goes vertically. So this is a 3 by 2 matrix. So go ahead and put a 3 by 2 below the first matrix. Okay, what's the dimension of the second matrix? 2 by 2. We got 2 rows and 2 columns. Put that next to each other, or but put that below the second matrix. Now, here's how we know whether the 2 matrices can be multiplied together. You see the numbers on the inside, next to each other here. These numbers have to be in agreement. Okay, if these 2 numbers are not in agreement, then we're not able to multiply matrices. Okay, so the inside numbers or the middle numbers have to be the same. Okay, so because they're the same, that's our check that indicates that these 2 matrices can multiply to something that we can produce. And here is the resulting matrix. The resulting matrix is going to be the outside numbers. So the outside numbers is the 3 and the 2. So that is what the resulting matrix is going to produce. This is going to produce a 3 by 2 matrix. Does that make sense? So the inside numbers is going to tell us whether it's possible, and if it's possible, we're going to rely on the outside numbers to identify the resulting dimension of our resulting matrix. Okay, so this is how I like to do this, and I think this is visually, it's very helpful as well. So you're going to put the left matrix first, but leave some room above because we're going to use that space for the second matrix. It's going to look a little weird. We're going to kind of put them kind of corner to corner here. So let me start here. Okay, so I'm going to put the first matrix kind of like in the middle of the page. I'm going to leave this space open for my second matrix. I'm going to put my second matrix here. I'm going to leave some space. 5, 9, 2, 4. Okay, it seems a little bit odd, but I want to kind of show us why I think this is helpful visually. Now, we know the resulting matrix is going to be a 3x2 matrix, so we're going to create a 3x2 matrix in this space here. Okay, 3 rows, 2 columns. So, but I want to leave space for what is in what we're going to combine these numbers in a very specific way. Okay, so there's my resulting matrix here. 3 rows, 2 columns. Okay. So how do these numbers combine? Okay, so this is how we're going to combine these numbers. Okay. The row, you see how we have 3 rows here? The first matrix, we're only going to look at it from a row perspective. We're going to do 4, 8, then 0, 2, then 1, 6. So we're always going to move from left to right. Now the second matrix, you're only going to go vertically from top to bottom. Okay. And what we're going to do is we're going to pair the numbers with each other. Okay. So every number is going to have a pair, and we're going to total them up in that way. So in this first space here, this is row 1, column 1. So that means we're going to take the information from row 1 of the first matrix and column 1 of the second matrix, and we're going to combine them together. Okay. We always move from left to right, top to bottom. So we're going to combine the numbers as we go from left to right, top to bottom. So the first numbers are going to pair with each other, 4 times 5. Plus, move on to the next number, 8 and 9. So that is how the numbers pair with each other. So the left matrix, you're always going from left to right. The top matrix, your second matrix, you're always going to go from top to bottom. Okay. We'll resolve these numbers a little bit later. Right now, we're just going to focus on trying to match the correct pairs. Okay, so now in this space here, this is located second row, first column. So second row of my first matrix, first column of my second matrix. Left to right, top to bottom. So the 0 pairs with 5, so 0 times 5. 2 with what? 9, yeah. Going down to this third row, first column, left to right, 1 and 5 pairs together, and then the 6 and 9 pairs together. Now, everything inside the second column is going to be involving the 2 and 4. Right? So to reach this space here, we're going to do first row, second column. 4 goes with 2, 8 goes with 4. Any questions so far? Okay. Second row of the first matrix, second column of the second matrix. Left to right, 0 pairs with 2, 2 pairs with 4. Okay, finally, third row, this empty space is located third row, second column. 1 goes with 2, 6 goes with 4. So I'm going to clean this up and add the terms together. I'm going to create my cleaned up 3x2 matrix. Okay, so 20 plus 72, 0 plus 18, 5 plus 54, 8 plus 32, 0 plus 8, 2 plus 24. Okay, any questions? Okay. All right, so let me do the second one with you and see if this makes sense, okay? All right, so first matrix, let's identify the dimension. What's the dimension of this first matrix? Remember, we always do row followed by column. So how many rows does this have? 1 row followed by how many columns? 3 columns. So 1, 5, 3. Okay, so it's important that that we, the order does matter. We say 3 by 1, and if you meant column and row, we have to say column first followed row first followed by column. Okay, what's the dimension of the second matrix? Yeah, 3 rows and 2 columns. So is it possible to multiply these 2 matrices together? Yes, because these 2 inside numbers match. Okay, if they don't match, then we'll just stop the problem and say not possible. But if they do match, we know that there is going to be a resulting matrix. So what's going to be the resulting matrix dimension? Good. 1 by 2. Okay, so I'm going to put my first matrix in this space here. And my second matrix, kind of like this in this upper corner here. Okay, leave some space because we're going to combine these numbers together. Okay, a 1 by 2. So my resulting matrix is going to have 1 row and 2 columns. So 1 row and 2 columns. So there's my 1 by 2. Any questions? So this empty space is located first row, first column. So I'm going to pick out row 1 from the first matrix and column 1 in the second matrix. Okay, so now how many pairs are we going to have? 3 pairs, right? -2 with 3, 8 with -1, and 4 with 5. Always move from left to right with the left matrix, and the second matrix go from top to bottom. Okay. This empty space is located first row, second column. So first row, second column. -2 with 4, 8 with 2, 4 with -6. Okay, so I'm going to clean this up here. -6 minus 8, -14, -14 plus 20, 6. -8 plus 16, that's +8. +8 minus 24, -16. Okay, any questions with the procedures?
You're always gonna go by like, for the first matrix, you're always gonna do it by rows and second.
That's right. We always go with, just look at the rows from the first matrix and just look at the columns for the second. All right, so let's go ahead and see if we can try on the next page on our own. See how much you can do on your own. Okay, and I'll follow up with the steps after you guys get it. Page 6. Everybody good with this page? I'll just come around and see whether this makes sense to do. Let me know if you have any questions about how the numbers are paired together. Okay, so now we can just total these values here.
Mr. Yang,
Yes.
wouldn't it be 4733?
Let me see, because that is wrong.
It's 43.
One is multiplying by zero, isn't it? Sorry.
It's zero, right? Zero.
I know. 8 plus 35.
Split eight, split eight into.
Oh, sorry, my bad. Finish second part.
Okay, any questions about the process? Okay, what happens if we switch the order of the matrices? Are we guaranteed that we can multiply if we switch the order? Depends, right? Depends, like, if I have a 3x2 multiplied with 3x3, would that work? 3x2 came first. It would, right? So, just because, I have a matrix that works in one order, it may not work in the second order. Okay. So, right. It really may not be possible if the inner dimensions do not match. A 2x3 followed by 3x3 is perfectly fine, but a 3x3 followed by 2x3 is all of a sudden an issue. We switch the dimensions of one matrix, it may become not possible, and it may change the answer, the dimensions may change. So, we already talked about this, but what has to be true in order for matrix multiplication to work, the number of columns from the first matrix must match the number of rows from the second matrix. The inner dimensions, the inside numbers have to be in. The last bottom part of the page is, does matrix multiplication result in the same product when the order is reversed? Probably not, right? Especially if we know that, that it's possible for one order to not even produce an answer that's possible. So let's just prove that to be true. The bottom part, go ahead and find the products of both matrices separately, right? You got 2x2 and a 2x2, but the order is going to be different in the way that we combine it. So basically, separate the two problems and then get more practice in terms of creating the multiplied matrices. Okay, go ahead and try that. I'll come around and see how you guys do, but we're just going to be practicing with this concept today. I do want to talk about word problems, which is a little messier, but at least if this process makes sense, we can dig into the word problems a bit. Any questions? Yeah, I do want to introduce word problems to us. So we'll do the top of the page on page 5, and then we'll do the bottom of the page on page 7, and that'll be the last thing that we do. And tomorrow we'll just get more additional practice with multiplication process. But any questions so far? Okay. Anybody still need this page? Give you another moment and then try to work through the top of page 6, sorry, page 5, the Catherine and Meg problem. Okay, all right. Top of page 5. Now, this is a bit of an incomplete problem. There's some information that's not provided, but I'll provide that information as we create the matrices. So Catherine and Meg spend their spare time working at Chick-fil-A, babysitting, and working on homework. Okay. Chick-fil-A pays them $8 an hour, $10 an hour for babysitting and homework. They don't get paid. Okay. When working at Chick-fil-A, they can't use their phones at all. While babysitting, they can send roughly 30 texts per hour. While working on homework, they can send about 40 texts per hour. Create hour schedule for each student. How can we set up matrix multiplication to calculate the pay and text hours for each activity for both Catherine and Meg? Okay, so let's start off with something that's not provided in this problem, and sorry, that's not provided in this problem here. So in order for us to calculate the how many texts and how much hours spent and how much they make, we have to know how much time they spend, and that's not provided in this problem. So I'm going to create that this matrix, first matrix, that's going to give us that information. So let's say Catherine spends 10 hours in 1 week working at Chick-fil-A, 15 hours a week working at a babysitting job, and 4 hours a week on homework. And then for Meg, 20 hours at the job, 2 hours babysitting, 8 hours for the homework. Now, if we want to create something to multiply by this matrix, we have to understand that the row of the second matrix must match the what? The column of the first matrix. So not only that, but the category must also be the same. So this is a 2 by 3 matrix. So the second matrix must start off with 3 rows, right? So if we're doing a word problem, we're always going to come to this scenario. We know we're on the right track if we can get this to match with this. So now we can use the information that's provided because we have the pay per hour, and then we also have the number of text that they're able to spend in each of their locations. So Chick-fil-A pays $8 an hour. Babysitting is $10 an hour, and homework is 0. The number of texts that they can send, they can't have their phone while they're working. For babysitting, however, they can send 30 texts per hour, and the homework, they can text 40 per hour. So this has the per hour information, and this has the total number of hours. So if we multiply this together, we can figure out how much Catherine makes, as well as how much she texts, and also how much Meg makes and how much she texts. So we're kind of merging this information so that we can just show how much they get paid and how much each texts. So we're just going to go through our multiplication process here. What's the dimension for this first matrix? 2 by 3. And the second matrix is 3 by 2. Okay, did this work? Yes, right. The middle inside numbers are in agreement. What's the resulting matrix going to be? 2 by 2. So now that I have my matrices set up, I'm going to just go through the same process that I've done before. Just put them kind of corner to corner. From first row, we're going to go from left to right. For the first column, we'll go from top to bottom. 10 times 8, 15 times 10, 4 times 0. This space here, 8 times 20, 2 times 10, 8 times 0. Okay, this is located in first row, second column. 10 times 0, 15 times 30, 4 times 40. Last second row, second column. 20 times 0, 2 times 30, 8 times 40. Total all this together. Okay, so 80 plus 150 plus 0. 160 plus 20 plus 0. Okay, 450 plus 160. 60 plus 20. So we're able to merge this information and see how much Catherine gets paid over the course of the week, how much Meg gets paid, how many texts she sends out, and on average, how many texts Meg sends out. Okay, we can only do this if the categories and information match between the column of the first matrix along with the row of the second matrix. Okay, if you guys can turn to page 7, we'll do one more problem. Number 7 below. Okay. Let's go ahead and use the space above number 7. We're probably not going to do. I have another worksheet that we'll work on. So I know I didn't give you a lot of space at the bottom. You guys can just we'll use the space above here for number 7. Okay, let's read the problem here. Different point values are awarded for each different shots in basketball. Use the information to determine the total points scored by each player. So these are the number of free throws, 2-pointer and 3-pointer that each of these players make. And then we can also assign the number of points per free throw, 2-pointer, and 3-pointer so that we can combine this information and actually figure out how many points each player scores. So what's the dimension of this first matrix? 3 by 3, right? 3 rows, 3 columns. Okay. What's the dimension of the second matrix? 3 rows, 1 column. Okay. Are these compatible? Yes. The middle numbers, dimensions are the same. And what's my resulting matrix? 3 by 1. Yep. So look how well these pair up, right? The column in my first matrix is free throws, 2-pointer, 3-pointer. The row for my second matrix is also free throw, 2-pointer, 3-pointer. There has to be that connecting connection between these two in order for these information to match, right? So those two not only have to match in dimension, but they also have to match in information. Otherwise, we're not producing information that's useful, right? But these have to match. So now that they match, we can go ahead and create our matrix dimension here. So Ray, Chris, Jerry. The resulting matrix is going to be a 3 by 1 matrix, 3 rows, 1 column. So look how well this information matches up. 44 free throws, 1 point each, 32 2-pointers, 2 points each, 25 3-pointers, 3 points each.
I think your screen's.
Oh, sorry, my bad. Realize it was. Total all that together, I'll do the math for us. Ends up being Ray scoring 183 points, Chris 178 points, and Jerry 200 points. Okay, any questions? All right, so tomorrow we'll continue with this practice. Okay. Don't forget your phones.
That's good.